we will now turn our attention to evaluating how well our regression line fits the data. And the statistic that we will use to determine this is the residual standard deviation. So the residual standard deviation is going to be given by the square root of the sum of the squares of the residuals divided by n minus 2. Now I'm going to go ahead and write out the formula for the sum of squares residuals, which is the sum from I equals 1 to n, or the sum over all the data points, y sub I minus y sub I hat, which is the point on the line that best estimates y sub I. And of course, we're going to sum the square of that difference, okay, divided by n minus 2. And so what you should see is that this formula looks a lot like our previous standard deviation formula, except for that y sub I hat is actually like the mean, okay? And we're going to divide by n minus 2, which is our degrees of freedom for this problem, instead of n minus 1. So here, what we have is essentially a formula that looks a lot like our standard deviation before. Now, the residual standard deviation gives us a sense of how far above or below the regression line the data points tend to be. Okay, so let's start with a calculation. Let's find the residual standard deviation for the global temperature data. Now, if you're using some sort of software, that will usually tell you what the sum of squares residual is. In this case, for our data, the sum of squares of the residuals is 0.5509. So our residual standard deviation is just going to be the square root of 0.5509. And then we're going to divide by our degrees of freedom for that data, which was 64. And that's going to give you 0.0928. And that is our residual sum of, or that is our residual standard deviation. Okay, so let's see how this looks on a graph of our data. Okay, so here we have a plot of our global temperature data. Okay, so change in global temperature versus CO2 levels in parts per million. And you can see we have our regression line. Okay, and then the black dashed lines are going to be plus or minus 1 standard error. Residual standard deviation, excuse me. Okay, so this distance here is going to be SE. And then this distance here is going to be SE. And in general, what we expect is about 68% of the data points will lie within 1 residual standard deviation of the regression line. So that sounds a lot like when we were saying that 68% of our data should fall within 1 standard deviation of the mean. Now it's 68% of our data points will lie within 1 residual standard deviation of the regression line, which is essentially the mean for this kind of problem. Okay, so I'd like to relate the idea of residual standard deviation to correlation, because correlation was another way in which we measured how good of a fit our best fit line is. So there's actually an approximate relationship between the residual standard deviation and the correlation coefficient. So r squared turns out to be the standard deviation of the y's squared, or the variance of the y's, minus residual standard deviation squared over the residual standard deviation squared. Oh, excuse me. That's wrong. It's over the standard deviation of the y's squared. Okay, so this is an approximate relationship that's true when n is at least bigger than or equal to 10. Now, let me rewrite this, okay, by dividing by the standard deviations of the y's squared. So I'll get 1 minus the residual standard deviation squared over the standard deviation in y squared. And r squared has a particular name. It's called the coefficient of determination. And since it's approximately equal to this difference between the standard deviation in y squared and the residual standard deviation squared divided by the standard deviation of y squared. Okay, so since it has that approximate relationship, it's going to describe the variance in y that is explained by the linear relationship between y and x. So in other words, if our regression line is a good fit, then the residual standard deviation will be approximately 0, and our r squared value, and therefore in turn our r value, will be approximately 1. Okay, so imagine that you're sticking in 0 here, and then r squared would be approximately 1. But if our regression line is a poor fit, then the residual standard deviation will be approximately the same as the standard deviation of our y's, and our correlation coefficient r will be approximately 0, because again the numerator here in that situation will be approximately 0. And so we can use our value of r squared to describe like how much of the variance in y we see that it's explained by the linear relationship between y and x. I'm going to show you that with the graph above in just a second, but first I want to just verify the relationship between residual standard deviation and r for our global temperature data. So r squared, okay, well, if we just calculate r squared, our r value for the global temperature data was 0.963. And so if we square that, you'll see that that's about 0.927. Actually, I'm going to write equal there. But if we look at the approximate relationship, which is supposed to be 1 minus the residual standard deviation, which is 0.0928, which we just calculated, divided by our standard deviation in y, which was 0.342, we saw that in the previous video, then what we get ends up being 0.926. And so you can see that the approximation for r squared is within 1/1000th of the true value for r squared. Now, what's the significance of r squared? Well, r squared is supposed to describe the variance in y that is explained by the linear relationship between y and x. So that means that 92.7% of the variance in y, which is in this case global temperature change, can be explained by the change, by the linear relationship with CO2 levels in the atmosphere. So when we say that r squared is 0.927, we're saying that 92% of the variation that you see in this graph. Okay, what do I mean by the variation that I see in this graph? Well, we have global temperatures that are all the way down towards zero. Okay, that because the change in global temperature since 1960 is around zero down here. Okay, all the way up to about a degree up here. Okay, so we have, when I say variation in y, you can imagine that I'm taking all of the data points that you see along here and I'm kind of replicating them as one data set. Okay, and then I'm asking the question about how much do the global temperature changes vary. Okay, in other words, like how big or how much variation do you see on this scale? Well, how much variation do I see on that scale? Well, 92% of the variation that I see on that scale is explained by the increases in CO2 levels in the atmosphere. So 92% of this variation that you see is explained by CO2 in the atmosphere. And so that's the power there of the R squared value in helping us understand what's the relationship between the two variables, okay? Because we expect there to be some variation. You see variation here around the line. There's all sorts of variation there around the line, okay? But only about 7.3% of that variation that you see around the line, right, is just kind of random variation or just a consequence of points being normally distributed around the line, okay? The main variation that you see, 92.7% of it, is in fact explained by that linear relationship between temperature and CO2 levels. And that's the importance of the R squared value. And that's why you see that it's often given on plots like this to help us understand how good of a fit for the data we have and how strong the linear relationship is.